This student book belongs to a set of student books which altogether provide a complete set of information to master SDMX. This student book aims at providing a general introduction to SDMX. It will look at its history, the components, the information model for data, and the information model for metadata. No specific prerequisite is needed to understand the content. Exchanging data requires a common standard, especially for statistical data. A common model is required to facilitate communication between databases. A number of organizations sharing the need for the exchange of statistical data and related metadata at international level decided to sponsor the SDMX initiative in 2001. Some of the benefits from SDMX standards are the following. It provides a common model to describe data and to structure the statistical content. It is an international standard. Its use avoids duplication of developments, saving resources, and the proliferation of proprietary solutions. It is an IT standard supporting the use of standardized tools by all the parties involved in the data exchange, at the same time reducing the reporting burden on data providers. SDMX stands for Statistical Data and Metadata Exchange. Version 1.0 was released in September 2004 and was approved as ISO technical specification. Version 2.0 of the SDMX standard was approved in November 2005 by the sponsors. The acceptance of SDMX at UN level is a major step forward towards a broad use of SDMX at worldwide level. Version 2.1 of the SDMX standard was approved in April 2011 by the sponsors. SDMX is a standard, but how is it implemented in real life? We will deal with three components of the SDMX standard: the SDMX information model, the content-oriented guidelines, and the IT architecture for the data exchange. Modeling data implies putting abstract objects along with real things. These abstract objects are metadata called descriptors in SDMX. Generally, the descriptors' names are explicit. Associating the descriptors with figures helps to provide a meaning to the statistical data. To see how it is implemented, let's take a real example from the tourism domain. Let's imagine we have to create a DSD for tourism statistics. Take a simplified table. 3 tourism topics over 3 periods. We can identify the following statistical concepts: frequency, in this case annual, country, tourism topic, time, the observation value, which is the actual single figure, the observation status, defined by footnotes such as estimated or provisional. Frequency, country, tourism topic, and time are required to identify the statistics. They act as dimensions. The observation status qualifies figures as an attribute at the observation level. The observation value, the actual figure, is what we call measure. The second table is a simplified formal definition of the corresponding data structure. We illustrate how this table can be represented as a statistical table. The statistical table in our example has three dimensions: country, time, and tourism activity. Let's consider only one, tourism activity, B010. If we fix the country, in this case France, we obtain one time series with a value for each given time period, in this case for each year. The values are the observations and correspond to the number of tourist campsites for France over the given time period. Now, if we fix the time, in this case the year 2006, we obtain one cross-section with a value for each country. The values are the observations and correspond to the number of tourist campsites for 2006 over the respective countries. Reference metadata is the information which normally describes entire collections of data and is not exchangeable with the data message. They are generally in a textual format. From a content point of view, they can be broken down into conceptual metadata describing the concepts, methodological metadata describing methods used for the generation of the data, and, finally, quality metadata describing the different quality dimensions of the statistical data. Reference metadata are structured according to metadata structure definitions that describe how reference metadata are organized. The objectives of the SDMX standard are to enhance the comparison of data and metadata analysis and encourage the maximum interoperability in the exchanges of statistical data and metadata. The standard comprises a set of recommendations in three areas: cross-domain concepts and code lists, statistical subject matter domains, and a common vocabulary of statistical metadata. Cross-domain concepts is the collection of statistical concepts which are relevant to many statistical domains. Each cross-domain concept has a unique identifier, a description, the context in which the concept may be used, and its presentation in the SDMX standard. Cross-domain code lists are collections of harmonized code lists which are relevant to many statistical domains. Each cross-domain code list has a unique identifier, a name, a description, and a list of codes. Each code has a description and annotation providing additional information. Both the cross-domain concepts and the code lists can be used in the data and metadata structure definitions. Statistical subject matter domains is a high-level classification based on the work of the United Nations Economic Commission for Europe on statistical areas. Examples of statistical domains are price statistics, national accounts, environment statistics, or education statistics. These subject matter domains may act as standard schemes against which similar domain lists of national and international organizations can be mapped to facilitate the exchange of data and metadata, as identifier frameworks for registering and searching statistical data on SDMX registries, as navigation aid for the identification and organization of corresponding domain groups. The metadata common vocabulary is a collection of statistical terms used within the other recommendations of the content-oriented guidelines, the cross-domain concepts and code lists, and the statistical subject matter domains. The added value of the metadata common vocabulary is in the opportunity of having one single entry point for accessing a variety of terms which are otherwise not always available or hard to find on the Internet. Now, we'll turn to another important module of the standard, the IT architecture. The IT architecture involves the standard formats for the data exchange, different architectures for data exchange, and the SDMX registry. In the push mode, the data provider sends the data to the receiving organization using email or file transfer. Once the file is received, an application based in the recipient's system processes it in order to upload it in a database for further elaboration. In the pull mode, when new statistical data is available, the data provider disseminates the data through their database or produces an SDMX ML file containing the data and stores it in a shared place. An RSS feed informs the collecting organizations about the availability of the new statistical data. The RSS feed contains the SDMX query message describing the new dataset and may contain the URL to the SDMX ML file. Then, the collecting organization may choose between two different ways to collect the statistical data. First choice, the collecting organization sends an SDMX query message to the web service. The latter fetches the data from the database and dynamically constructs the SDMX ML file, which is then returned to the collecting organization. Second choice, the collecting organization downloads the SDMX ML file directly from the shared place via the URL if it resides in the RSS feed. A hub is based on the concept of data sharing. Data is not previously collected and stored in a central repository, but is directly accessed from the data provider's databases through the central hub upon request of a data consumer. The data consumer browses the hub to define the data set of interest via its structural metadata. The hub converts the user's request into SDMX query messages and sends it to the National Statistical Institute web services. The National Statistical Institute's web services convert the SDMX query into a set of SQL queries from the National Statistical Institute's databases, dynamically construct the SDMX ML file, and send them back to the hub. The hub assembles all the SDMX ML files received from the National Statistical Institutes and presents the results to the user in a readable format. The registry is a metadata repository accessible over the Internet, extranet or intranet. It provides information such as the concepts and DSD needed to facilitate the reporting, collection and dissemination of statistics. The SDMX registry has a web service allowing third-party applications to interoperate with the registry by exchanging SDMX ML messages. The Eurostat SDMX registry also has a graphical user interface. The SDMX registry does not store any statistical data. Any application that requires data has to query the registry in order to know how to access and download the data and metadata directly from the data provider's website and how to interpret them. To summarize, SDMX is an international standard. It has three components: the SDMX information model for data and metadata, content-oriented guidelines, and technical specifications for exchange. Its implementation is facilitated by freely available software tools. SDMX is sponsored by 7 international organizations since 2001. If you want to know more about it, look at sdmx.org, which provides the technical standard and guidelines, and also links to other resources, such as the Eurostat SDMX InfoSpace and self-learning tutorials on specific topics.